And so we were talking about the regulatory enzymes, and we were all the way to looking at these enzymes here, right? So we have these irreversible steps, 1, 2, 3, and in each case you have different enzymes that are regulating the glycolysis versus gluconeogenesis. And so right now we're talking about this one here, right, the fructose 1,6-bisphosphate and phosphoglucokinase. So I want to remind you that these actually have a 1 after them, and they're distinct from enzymes we're going to talk about in this lecture that have a 2 after them. So the first few slides we talked about at the end of last lecture, but I'm just going to go through them really quickly to get you back to speed. So we're talking about that reaction, right, where we can actually have the formation of glucose or glycolysis to make pyruvate. And so these are differentially regulated. So if you have ATP, right, you don't actually need to do glycolysis to make ATP. So it's negatively regulated. So a lot of this is just understanding what are your end products, when would you need to do something. And on the other hand, when you have a lot of AMP, right, you're actually going to be inhibiting gluconeogenesis. So there are other ways besides ATP, ADP, and AMP to regulate these 2 differential reactions. And we started talking about this last time, this fructose 2,6-bisphosphatase. So like we talked about before, the bisphosphate, we have 2 phosphates on 2 different positions, which is what the bisphosphate is about. And it's not an intermediate, but it's a regulatory compound. And it differentially regulates these 2 processes, and we're going to look at that. So it positively regulates glycolysis, and it negatively regulates gluconeogenesis. So you would expect that when glucose levels in the blood, right, are high, you would have glycolysis, and when they're low, you would want to form, right? So it makes sense that if this is positively regulating to use the glucose for making ATP, that this would be a positive regulator while negatively regulating formation of glucose. So we had this theme of allosteric regulation, and here we have it again. So in this case, you're looking at the influence of the substrate, fructose 6-phosphate, on the PFK1 activity. And when you have this allosteric effector, right, it's increased significantly. Without it, it's basically afunctional, even when you get to fairly high levels. So this is really the driving regulatory compound for glucose, for PFK1. Okay? And so if you were to get a graph like this, you should be able to tell me, right, how it was regulating each of these activities. So the opposite is happening for FBP1. In this case, right, when you don't have any, you have this really high affinity. And so what they're showing you here, right, is that a particular concentration with F26BP, you have nice activity. Without, you have some activity. Without, you have really high activity. So how does this, just to show you again, how is this modulated? So I told you that this was not an intermediate, so then your first question should be like, well, so how is this made, and how is that level controlled if it has such a big influence? So basically, it's made in the liver, and we know the liver is really important to controlling the amount of glucose, and whether it's going to the blood, whether it's going to storage, how it's being utilized. So in this case, right, we're confusing you by having PFK2 and FBPase2. So these are actually now different enzymes from PFK1 and FBP1. In addition, FBP1 and PFK1 are separate enzymes, and these 2 have these enzyme activities, but they're actually a bifunctional enzyme. So they're on one polypeptide. So what's interesting about them is, right, the kinase activity. So whenever you see that kinase, you know it's adding, right, the phosphate, fructose 6-phosphate to fructose 2,6-phosphate. And whenever you have the phosphatase, you know it's removing it. So again, this is a theme that, once you know the language, you can figure this out yourself. So the key is, right, how do we control what's going to these different fructose 6-phosphate versus fructose 2,6-phosphatase. And here, right, you can see that they're making this unusual compound, the regulatory one, fructose 2,6-bisphosphate, instead of here, right, where they're making 1,6-bisphosphate. So it's really similar, but the enzymes have a slightly different active site to make a slightly different product or use a slightly different substrate. Okay, so, and then this activity is controlled by hormones, glucagon and insulin, which we'll talk about more in a minute. But basically, glucagon decreases the fructose 2,6-bisphosphate. So basically, it's decreasing this. So if it's decreasing it, it's promoting gluconeogenesis. And with insulin, and we're going to have some lecture slides that pull it all together. And with insulin, it's increasing it, so it's promoting glycolysis. So if you look back here, right, in this slide, you can see that if your activity is, if you have more F26BP, right, you're promoting glycolysis. And if you have less of it, you're actually promoting gluconeogenesis. So how is that protein actually regulated? The protein here that's influencing these activities. So they're regulated by phosphorylation. And this is a case where it's not about putting a phosphate on a substrate like fructose 1,6-phosphate to fructose 1,2,6 or something like that. It's actually about putting the phosphate onto the protein. And we mentioned last time that these can only happen on a couple types of amino acids. So on a serine, a threonine, or a tyrosine, because they have that OH group. And then you can put the phosphate group on with the kinase, right? So that's adding the phosphate, and then the phosphatase is removing it. So in this case, this is a phosphoprotein phosphatase. Sometimes in the biochemical name of the enzyme, it doesn't bother to say phosphoprotein, but this one is giving you a nice indicator that it's actually putting or taking off, in this case, taking off the phosphate from a protein as opposed to a molecule, like a glucose 1-phosphate. And here, this is a protein kinase putting the phosphate group on. So we already talked about that. So what's happening here is actually you have regulation by glucose, which is influencing insulin and glucagon, right? These two hormones that's controlling the phosphatase versus the kinase activity. And then the kinase versus phosphatase activity is what's controlling the activity of your bifunctional enzyme. So this is just one way of writing a bifunctional enzyme. So up here, when it is not phosphorylated, you actually have the PFK2 being active, you increase F26BP, and you have glycolysis. On the other hand, right, and that's occurring, right, when you have, so increasing, so I always have to double check when I'm talking to you, right? So if you're increasing glycolysis, you want to have your glucose level being high, right, so that you can actually be using it to make ATP and other things. So in that case, right, your insulin, your glucose level is high, your insulin is promoting the phosphatase, and it's in the inactive form, phosphatase, no phosphate group here, right? And that's stimulating F26BP and glycolysis. So you really want to kind of go through the rationale for each thing to make sure you're understanding it. The opposite is here, right? When you have blood sugar that's low, you want to actually be making blood sugar that's low, you want to be increasing glycolysis. So in this case, you're stimulating through glucagon, your cyclic AMP. That is adding this phosphate group on, and then in this case, the glucose is being made. So here you have gluconeogenesis happening in the liver. We're going to keep seeing this in a couple different forms as we talk about glycogen, you can go back over this later too. So the last enzyme that we haven't talked about yet is the pyruvate kinase. So we had talked about hexokinase, the phosphofructose kinase, and now we're at this step, okay, this final step going to pyruvate. So again, whenever you're looking at controls, you want to look at those 3 irreversible steps. You know that they're going to be highly regulated. So in this case, we have, again, we're having these similar kinds of regulation. We're having regulation by phosphorylation, but we have 2 different types of the enzyme. So we have one that's only in the liver and one that's in everything. So the one that's in everything, we'll actually talk about first. So the one that's in everything, it has this classical feedback. So for pyruvate kinase, right, if you have it active, it's happening right here. It's catalyzing this reaction from phosphoenolpyruvate to pyruvate, and generating ATP, right, is the final part of glycolysis. So this is actually feedback regulated by positive precursors. So this is actually, stimulating it. So if you have enough of the precursor, those concentrations are high, you're stimulating it. However, if ATP, this should be right here, if ATP is high, you're inhibiting it because you wouldn't really need to be making as much ATP, so that wouldn't be inhibitory. So the reason there's a little blank here is your book goes into other regulation, which I'm not stressing. So I'm stressing ATP, which has been a theme throughout. On the other hand, so this is happening in every type of glycolytic tissue, including the liver, but then only in the liver, you have this additional regulation. So basically glucagon, through a pKa activity, which we can look at. So this is the protein kinase, and this is a phosphatase. So again, the kinase, right, would be putting on a phosphate, and you can see it put on here. And then the phosphatase is taking off the phosphate. So in this case, when it puts on the phosphate, it's making it inactive. And basically, it's stopping that last step at low blood sugar. So what it's doing is, if there's low blood sugar levels, it's a way of controlling it kind of at the last minute to say, okay, we don't want to use up ATP, we want to actually be able to slow down the rate of this reaction in order to have more glucose in the bloodstream. And you're going to look at that more in a minute, and you'll notice that glucagon is regulating this. So these are the same study aids that were listed before for 4 and 5 in terms of what you need to go over. And I'm pretty clear about what structures you need to memorize and what you don't. And then the problems are always the problems at the back of that chapter in version 6th edition. So now we're going to move on to glucose utilization. So we've talked a lot about glucose. So we've talked about glycolysis. We've talked about gluconeogenesis. We've talked about the pentose phosphate pathway, but we haven't talked about this control, right? To make the storage forms of glucose. Of glycogen. And in plants, that's starch, which we're not going to focus on. We're going to focus on glycogen here. So we want to know, right, how do we control whether glucose is used and how it's used, and then whether it's stored. And not only does it go in one direction in storage, but it goes, as we know, in both directions, right? So here, gluconeogenesis, here it's like depolymerization or breakdown of glucose. So if we look at glycogen, it's the storage form of glucose, and it's we're going to focus first on degradation. So basically we're going to get glucose and glucose 6-phosphate, which we can then convert to pyruvate, or we could use it in other things, right, like the PPP, pentose phosphate pathway. So what does glycogen look like? So it's the major sugar storage in animals and bacteria. In plants, it's starch. So in the liver, it can be 10% by weight, so 10% of the liver mass by weight, and it's a reservoir for the brain. And we already saw that PET visual, right, of like how much glucose we need in the brain. And then in the muscle, it's a reservoir for activity. So if we look at this structure, this is a sugar polymer, and so it has a number of things. It has these alpha-1,4 linkages. So if we look at this structure, right, the 1,4 linkage will be 1, so that's 1, and then here it's 1, 2, 3, 4. So that's a 1,4 linkage. Okay. And then you have branches, which are the 1,6 linkage. So again, we're at position 1, and here we're at 1, 2, 3, 4, 5, 6 to get this alpha-1,6 linkage. And so there are a couple major enzymes that break down this huge polymer. And this polymer can have up to 55,000 glucose residues in a glycogen. And we talked about like a number of lectures ago that this could reduce the osmolarity, and so you can actually store this polymer. So instead of it being 0.4 molar, if it was all free sugars, it's actually 0.01 micromolar. So you're not really increasing the osmolarity. So there are a couple enzymes involved in this: glycogen phosphorylase, a debranching enzyme, and phosphogluconease. So these two convert it from glycogen to, you'll see, glucose plus glucose 1-phosphate, and then this one converts between glucose 1-phosphate and glucose 6-phosphate. So in the first part, what we're doing is cleaving the alpha-1 part. And so what will happen is you'll actually just get cleavage right at this end, and you'll release. So this is a glycogen phosphorylase. In this case, you're adding this phosphate, but it's coming from this TTP cofactor. Because otherwise you'd be like, well, it's not a kinase, and it's not, where's it coming from? So when you also see this word phosphorylase, it's also a clue that you're getting a phosphate from somewhere. And in this case, it's coming from this TTP cofactor. So here, this is breaking off, and you're getting this to glucose 1-phosphate. Again, it's the phosphate's on the 1 position. And then now you continue to have this chain with the non-reducing end. It's just shortened by 1 glucose molecule. So this can go on and on and on and on until you hit 4 residues from a 1,6 linkage. So this just has to do with how the enzyme is able to recognize the conformation. And so basically it's going to be going cleave, 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 each time making a single glucose 1-phosphate molecule. So remember, this is not glucose 6-phosphate. It's not going to feed right in. It's glucose 1. So, and then you have your chain here. So once you get to the 4th position, so basically for what you need to know is to understand this processivity. So once you get to this 4th position, then you're actually having an enzyme called a debranching enzyme, which has 2 activities. So the first thing it does is it cleaves, it does a transfer here, and then it cleaves off this glucose. So you have lots of glucose 1-phosphates and then a glucose, right? So actually, the number of single glucoses is telling you how many branch chains you have, right? So again, this is the kind of question that makes you think just one more step, right? How could I easily tell how many branch chains, how many glucoses did you get instead of glucose 1-phosphate? Because now this is going to go bump, 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 right? So back to the phosphorylase. So you have the debranching, which is a transfer, a cleavage, and then you go back to this phosphorylase, and you cleave, 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 cleave. And then you'll go to the next branch site, etc. So now we're left with a lot of glucose 1-phosphates and a few glucoses. So we have to convert the glucose 1-phosphate to glucose 6-phosphate for glycolysis. Or for other things, right, like the pentose phosphate pathway, or even gluconeogenesis. So in this case, what's happening here is, and you don't have to memorize this reaction, I just want you to see it. So again, this is in this enzyme, a phosphoglucomutase. You can guess at what it's doing. So the glue, right, it has to do with the glucose. The phospho is that phosphate group, and mutase is actually, it's just changing where it is. So you're using a phosphate group that's on a serine as the donor. So it actually needs this serine that's phosphorylated on the protein. And then it's attacking here. This is the phosphate that's already, here's your glucose 1-phosphate. This is coming in, and now this phosphate is going on to the serine in the protein. So this is recycling, right? You'll always have this phosphorylated serine, and you have a phosphate on your glucose, but just at a different position. And then once you have that, it's ready to go. So it can go to glycolysis, to phosphohexose kinase. It can go to PPP, the glucose 6-phosphate dehydrogenase, or it can go to gluconeogenesis, the glucose 6-phosphatase. All right. So when we have conversion to glucose in the liver and the kidney, right, we can have this glucose 6-phosphate transporter bringing it in, converting it to glucose, and then having it brought into the bloodstream. So I'm not going to focus actually particularly on this one. I just wanted you to get a feeling for how this might happen. What I want to focus on is the differential regulation of the synthesis and use of glycogen. So we talked about the degradation, and now we're going to talk about the synthesis. So what is the glycogen? So you already know what it is, right? It's a glucose polymer with the alpha-1,4 linkages and a couple branching alpha-1,6s. So you have your glucose group, and then it basically has to be activated, so you get energy-rich phosphate ester, and then that's what gets transferred. So you'll see in the next reaction that you have your sugar phosphate. You're not going to be needing to push electrons. I just want to show you what happens. So that's attacking here, coming over, and you're getting your sugar with your 2 phosphates, your ribose and your base. So you have a sugar phosphate that starts here. You have an NTP, right, a nucleotide triphosphate. It can be either A or U, and then that's going to your NDP sugar plus phosphates. And you can see that this has a very negative delta G. Okay? It's really being pulled by this phosphate release. So here, right, with glycogen synthase, you're elongating this. And so every time you go through this, you're elongating with N+1 residues. So this is coming in, and you're adding the sugar here, and you're releasing the phosphate. So for this part, I'm not stressing actually the reaction mechanism, but the regulation. And so the next slide is the one, and also just the idea of how it's processed. So if you look at the next slide, right, when you have the branch synthesis, You have the non-reducing end, you have the 1,4 linkages, and then here you have this core, and then the glycogen branching enzyme is what comes in to make this branch point here. Okay. I thought I was going to do something else faster. Okay. Oops, sorry. So we're right here. So then here you're in your final step, right? So you have this chain extending activity, and then you just keep going over and over and over. And because I'm not focusing on this and all the electron transfer, I just want you to like be familiar with the processivity of it, the general idea of it. And one way to think about it is, because we looked at how it's broken down first, it's kind of the reverse of that in terms of how it's synthesized. You just first have to activate it with that phosphate and that NTP, and then you can actually do the reaction, and then you can do the branching part with the alpha-1,6, and then you keep going. So finally, in the end, right, you have this glycogen structure, and I don't want you to worry about the glycogenin, but just to think about this branching structure where you have these different tiers, right? So we talked about 55,000 molecules, right? So you'll have the initial chain, and then every 6 to 7, you'll start getting a branch, and then you'll have another one coming out every 6 to 7, you'll get a branch. And so the real idea of this is that you have very low osmolarity because you have very few reducing ends, and in fact really one reducing end, and it's fairly inaccessible until you have the enzymes that can come down and break it down. So now we're going to get to the next lecture, which talks about the regulation, which is more of our focus.
I brought bread.
I just ate bread.
To go.
Oh, to go? Okay, sure. Vegan?
It sure is. That's vegan.
Oh, you know less?
So we really briefly talked about glycogen synthesis. We talked a little bit more about glycogen breakdown. And now we want to look into its regulation. So this is a really busy slide, but there are a couple really simple points to it. So when you're looking at glycogen regulation in the muscle versus the liver, you have two different hormones that are controlling this. So one is epinephrine, which is happening in the muscle, and one is glucagon, which is in the liver. And basically, in order to activate this glycogen to glucose 1-phosphate, you have a cascade happening. And that cascade is phosphorylation dependent. So it starts out with activation of this, basically what you want to get to is here, activation of this protein kinase. And the way that that gets activated is by cyclic AMP. So adenosine monophosphate, right? So you have 1-phosphate, adenosine, and your sugar group. And then it's cyclic, right? You can see that it's cyclized. Have all of you seen cyclic AMP before? Raise your hands. Yeah, okay, good. So in this case, cyclic AMP is coordinating the activity. And cyclic AMP is actually a regulator, a really common regulator in bacteria and across all different systems. And so it's a little bit less common than ATP, for example. And so in some ways it's often used really as an energy sensor that's even more specific than ATP. So in this case, right, we're controlling the cyclic AMP levels by these different hormones. And one of them is acting in the liver and one of them is acting in the muscle tissue. So when you have this activated through the hormone, we're not going to go into exactly how that happens, you have more cyclic AMP, and then the cyclic AMP activates the protein kinase. And then the protein kinase, when it's more active, then it's rapidly turning over, and it is then activating this phosphorylase B kinase, so another kinase, then it gets even more active. So every time, right, there's like a tenfold increase or even more in activity. So this is what's been measured in terms of the activity increases, but they think in vivo that the measurements aren't perfect, so they think it's actually even more of an escalation. And so then finally, right, your glycogen phosphorylase is activated, and then that's converting, right, your glycogen to glucose 1-phosphate. So that was the reaction that we looked at before. So it gets to the point where you're making 10,000 molecules of this. So this is an amplification loop, and it's a really efficient way. So I don't know if you guys have learned about MAP kinase cascades in other classes, or even in the first part, anyone? Okay, so again, that's another way of amplifying using phosphorylation as an amplification tool. So in this case, right now, we have glucose going to glucose 1-phosphate, and so basically then, this can then be used to go into glucose, to the blood glucose, right, so in the liver, or it can be used to actually make ATP in the muscle. So when they're talking about like flight or fight, right, so in the muscle, you want, basically to be able to power your muscle, but then you also need glucose in the brain. So these two things are actually co-regulated. And there are special enzymes that are actually controlling these, and basically that are responsive to this original regulation by epinephrine versus glucagon. So let's look in this a little bit more detail. So if we look at the, here's the phosphorylase, right? So in this case, phosphorylase A and B forms. So this is in the muscle. So in this case, it's less active when it's not phosphorylated. So again, if you had this and you had to like look at whether it was less or more active, right, and I gave you part of it, you would be able to figure it out. So if you have glucagon in the liver is positively regulating the kinase in this direction, this gets phosphorylated and it's active. Okay. In this direction, if you are activating here, it's less active. So in resting muscle, right, this is less active. And when you're exercising and you need this, then it's more active. And so glucagon can control that in the liver, and then in the muscle you have epinephrine, calcium, and AMP. And the reason AMP is controlling it is, again, because in the muscle you want to be making ATP from glycolysis, and so AMP, if those levels are high, it means you need more ATP. And whenever you see this, right, this is showing you that an enzyme is phosphorylated. And then here it's actually showing you the position that's phosphorylated. We actually now know the motifs that are recognized by a lot of these kinases and phosphorylases, and you can even plug your protein into basically a database that'll predict phosphorylation sites and the type of kinase or phosphorylase that would work on them. Then you can test it experimentally. We also we're in a really exciting area of biology. So many people are doing mass spec studies too, where they pull down proteins under different conditions, and they can see whether they're phosphorylated or not, and they can see where. So you can have a predicted site, you can search the literature, see that it's actually phosphorylated on that site under particular conditions, and then go about and test a hypothesis. And in fact, in my lab, we've done that. We didn't even have to do our own preliminary data. It was out in the literature, and then we could take it to the next step to put in for a grant. So there's a lot of information out there if you can think about the hypothesis. So in the liver, what's happening, so we were just talking about the muscle, right? In the liver, it's a little bit more complicated, right? So in the muscle, it's all about generating ATP, or it's primarily about generating ATP via glycolysis. But it's a little bit more complicated because you can have a situation, there's like this additional level of control because you want to control glucose levels in the blood. So here you have this phosphorylase A that's phosphorylated, and it has two allosteric sites that are empty. So it's very active here. It has these empty sites. So if you have glucose, so let's say that somehow quickly you ended up having more glucose in the blood. In the liver. So at that point, right, so it could be like from eating something, it could be from whatever, that you suddenly had more glucose. Then this can rapidly respond to that change through allosteric binding. So specifically glucose fits in this site, here and here, two glucoses. And then when that happens, you get a conformational change where suddenly the phosphates are accessible. So here they're buried, and now here they're accessible. And once they're accessible, then it can be phosphate. Basically, the phosphatase can take off the phosphate, and then it's inactive or less active. So the way it's drawn here is to hide the phosphate so that you know that it's no longer active, and it's only when you have the glucose that it then, I didn't mean active, it's not accessible. So then it's only when you have the glucose binding, you get an allosteric conformational change, the phosphates show, and then this enzyme here can actually act to take off those phosphates, and insulin increases this activity. So what you're doing is you're slowing down glycogen breakdown when you have high glucose, right? High glucose in the blood. So you started at the top of that pathway, but then by the time you get to the bottom of that pathway, if there's high glucose, it'll slow it down. Okay? So it's trying to keep your glucose levels in homeostasis and also not to be wasteful. So just to look at this type of regulation again. So a couple themes that we're seeing for glucose, and this is true for a lot of metabolites. We don't only have regulation by allosteric mechanisms, but we also have regulation by transport. So here we have regulation, so under conditions where insulin is increasing, you'll actually get an increase of the glucose transporter, GLUT4. So more glucose will go into the muscle cell. And then you'll also have an upregulation of the activity. So that's what that's showing, is just that you're getting more of the transporter here. So it's a positive regulation. So if you don't get it transported in, right, you can't use it. So that's a critical level of control. And then hexokinase is actually synthesized, so it's controlling the synthesis of hexokinase. So again, if it's controlling the synthesis, that's typically at the level of like transcription factors and other regulation. Which you'll get into more in the next part of the class. And then from here, right, we have these conversions, and then here it's actually a covalent alteration that's happening. So it's promoting this covalent alteration of glycogen synthase. We're gonna look at that in the next slide. So your book likes to talk about metabolic control and metabolic regulation. When it's talking about control, it's talking about flux, and when it's talking about regulation, it's talking more about like allosteric. But those terms are a bit arbitrary, so I will not be like using those terms on the test. I'll be just asking you for specific mechanisms. So the regulation of glycogen synthesis. So we talked quite a bit about the degradation of glycogen. And we briefly talked about how glycogen was made. And so now we're going to talk about just I want to focus more on the regulation of how it's made. So it's, of course, the opposite of glycogen synthesis. Glycogen synthesis would be the opposite of, glycogen degradation. So in this case, we have glucagon, which is stimulating glycogen synthesis. So we have a kinase here, and I think it's most easy to go here, right? So when glycogen synthase is active, it's not phosphorylated. So it's the opposite of the degradation. Okay? So for the degradation, when it's phosphorylated, it is active, and here when it's not phosphorylated, it's active. And so how is that phosphorylation controlled? So basically we want to talk about this phosphoprotein phosphatase and how this is controlled, right? So the way it's controlled, there are a number of ways, I should say. So first of all, it can be controlled by this enzyme, this G3K3, glycogen synthase kinase 3. And that's kind of unusual. It has to be primed by this casein kinase, and then it also can be blocked by insulin, but if it's primed and active, then it can add on these phosphate groups to the enzyme, right? And then that makes it inactive. Okay? So inactivation happens via glucose. Inactivation happens via this glycogen synthase kinase, because the phosphorylated form is inactive. And then activation happens through a number of mechanisms. So activation happens through insulin, it happens through glucose 6-phosphate, and it happens through glucose. So if you're thinking about it, right, if I just had glycogen synthase at like inactive to active, and you thought about it, when would you want to make it active? Well, if you have enough glucose, yes. If you have enough glucose 6-phosphate, yes. Right? If you have insulin, you might not remember that off the top of your head, but you will, right? Then it would be yes. Whereas the others, the glucagon and the epinephrine, would not be promoting this. So putting it together in the liver, after eating, you have high blood glucose. Okay. So you would be increasing the transport of glucose, right? You have the increase in glucose, increase of the hexokinase, and this is actually talking about synthesis. We talked about that in a couple slides ago, and all the other enzymes, right, involved in glycolysis. So we're increasing glycolysis. So high blood glucose, right, we can make ATP, that's great. High blood glucose, right, we would probably also want to increase glycogen synthesis because we have enough glucose, so now we can store it, right, for when we don't. So again, in this case, right, what's happening here is you can get that transport and you can have that glucose and glucose 6-phosphate feeding into glycogen synthesis. So depending upon the conditions, it can be going to glycolysis versus synthesis. It can also come in, this is just showing another way it's regulated, which is through insulin. And here, again, you're promoting it through these controls over the glycogen synthase enzyme that we talked about in the last slide. A lot of these controls are through phosphorylation, right? So particularly on this side we talked about, right, that it's phosphorylation control here, phosphorylation control here. So when insulin is up, when you have high blood glucose, you don't want to break down glycogen because you already have enough glucose. And so in that case, right, you're actually increasing GP1, decreasing this kinase activity, and decreasing the glycogen phosphorylase. So you're always having this opposite regulation between glycogen synthesis and glycogen usage. And when you have high blood, you either want to synthesize it or do glycolysis, and don't need to break it down. So let's look at the opposite. And then I put this here because this was actually to help you relate back to the earlier lecture when I talked about regulation of hexokinase, where I said it could also dissociate from the regulatory protein. So just to remind you to link these lectures, okay? So just have a couple more like this. So now we're looking at it in the liver under the opposite conditions, where we have, in this case, right, we have low blood blood glucose. So we're gonna follow it. What would happen under low blood glucose? We would actually want to make glucose, right? So in this case, we would want to break down glycogen. We would not want to be making glycogen, so we're decreasing synthesis, and we're decreasing glycolysis. So it's really all about promoting making glycogen, making glucose, sorry. And again, this is regulated by phosphorylation. And I'll let you work through these with the other slides. I'm just trying to pull it all together and help you think about it so that you know what to look at as you're moving through it. So then pulling this all together in the muscle and in the liver, right? Under low sugar in the liver, glycogen is converted to glucose 6-phosphate and glucose to make blood glucose, right? You can also have gluconeogenesis to make glucose. So when you have low sugar, you're either breaking it down or from glycogen, or you are doing gluconeogenesis from pyruvate. Here in the muscle, you don't have a glucagon receptor, so instead what you're doing is you're just going from glycogen to pyruvate to make that ATP. So in the muscle, it's about ATP, and in the liver, it's about both glycolysis, but mostly, in the liver, it's mostly about actually making glucose so that you can put it into the bloodstream. So I have a clicker quiz. I hope we can do it quickly. Can you see it? Yeah. So I'm going to start it now. And I'll move this over. I'll try to make these
A is phosphate glucose, not just regular.
instead of the N.
Senses,
So remember, you can talk. This is a little bit more complicated.
Does it activate the enzyme? See the first part.
D? That's really actually sensitive. It's not A. It's not A. Yeah,
I think
it's
it's D.
D. Hold on.
I think it's D.
It's D? Do you think it's D?
I don't think it's E.
It's definitely not B, C, or D.
It's not A for sure.
I think it's E. I don't
E?
know why all this
You're saying?
Phosphorylation activates the enzyme.
Ah, someone. What? What? I can't hear you. Hold on.
Let's just do it.
We're running out of time, so you'll want to vote now.
A? I don't know.
And if you have trouble, right, narrow it down to 2, and then you can discuss with your neighbor about the 2. So there are a couple, right, you can leave off from the very beginning. And because we're running out of time, I'm just going to show you, oh, I have to put it back in here. So the answer,
Oh, yeah.
oh, sorry. Yeah, so good job. So that was more complicated, so I'm really happy that somebody.
I need to review that again. I need to review that.